Dear students, we are resuming our discussion of circular motion. In the last lecture, we started our topic, vertical circle. By vertical circle, we mean an object moving in a circle, but in the vertical plane. That means it starts somewhere at this position initially. Let's say it is a stone tied to one end of a string, and when it is whirled in this manner, it starts from this position, moves towards the top, following this path, slowing down a bit, reaching the top position here, and then it continues back along this path, accelerating, coming back to its initial position. There are at least two positions of interest here. This is our initial position. Let's say we label this position as A, and this is a position during its motion, which we often call the top of the circle. This position is labeled as B. When the object is whirled along a vertical circle, it has maximum speed here. Obviously, the object, when it going towards the top, slows down and it has minimum speed at this position. If I label this position, this speed as VA and this speed as VB, we will be in a position to derive expressions for the centripetal force that acts at this position A and the centripetal force that acts at the position that is the top of the circle. At position A, when the object is moving in the vertical circle, this is the position where we expect the tension in the string to be maximum. The tension in the string provides the centripetal force, but it is maximum here because there are two forces which are at work at this position and that produce tension in the string. We can write this tension T equal to weight, which is acting vertically downwards, plus mv square over r, and this v is VA. So this expression tells us what is the tension in the string. That is sum of two forces. Both forces are acting away from it. The centripetal force T is actually the combination of these two. In the absence of weight here, the tension would alone be equal to mv square over r, as we learned during the discussion on horizontal circles. But during the vertical circle, weight is also important. And since this weight is acting away from the circle, this must be countered by the tension in the string as well. So one thing is obvious: when the object is moving in the vertical circle, this is the position where the tension is maximum, and therefore this is the position where the string is most likely to snap if it cannot withstand that much of tension. That means in order to provide this centripetal force, it must be strong enough. If this sum exceeds this tension, the string will obviously snap. So this is our equation for the position that we have labeled as position A. This is the bottom of the circle. Now for position B, When this stone moves towards the top, it slows down, and this is the position where its speed should be certain minimum. If it is less than that certain minimum, the object will not be able to complete the vertical circle. It will reach here, but it will be unable to complete the circle, and maybe it falls like this. So in order to complete the vertical circle, an object must be given a certain speed VA here in order to enable this object to have that minimum speed at this position, so it continues and moves along this path and does not fall vertically. So tension in this case, if I show the tension towards the center again, this is TB now. This was TA, and now the tension in the string is TB. But it is not the tension alone which is vertically downward at this position. The weight is also acting downwards, this time like this. That means I must add mg to this side of the equation and write mv square over r on this side of the equation, and this v is vb. So these two equations clearly explain the relationship between the tension in the string and the weight and the expression for the centripetal force that we have been using for the horizontal circles. In the last lecture, I used this expression to calculate the minimum speed which the object must have at this position in order to complete this circle. And for that, we assumed tension to be 0. That means for minimum value of the speed VB, tension TB may be taken equal to 0. And when I take this 0, it is easy to see that this expression VB becomes equal to GR under root. When I take this term equal to 0, mg will become equal to this expression, with m gets cancelled on both sides, and r is on this side will be as gr, and vb will be equal to gr under root, because vb square will be the product of g and the radius of the circle. So this is the standard expression for the minimum speed required. Now, with this background, we should be in a position to discuss at least 2 questions which appeared in the past papers. One question appeared in May-June 2010, and let's discuss that first. Suppose the stone that we have used in this case has a mass of 500 grams. 500 gram mass is attached here, and this is a stiff rod. This is a stiff metallic rod, and at the end of this we have tied a stone with a glue, and it is stated in the question that this is the stone tied to one end of the rod with a glue, it can withstand a maximum force equal to 18 Newton. And if that exceeds then 18 Newton, it snaps. So first thing we can guess is 18 Newton is that maximum force which must be provided by the glue at this position, and at all other positions this required force will be less than it. So the chances of snapping is at this position if it snaps at all. As this rod is made to move in this manner with a constant angular speed that we need to calculate. We need to calculate omega. And one more piece of information provided is the length of this rod. The length of this rod, that means radius, that is equal to 20 centimeters. So with this information, the equation that readily comes to mind and becomes relevant is equation that we wrote for position A. Let's label this equation as equation number 1. So when I write this equation here, this is the force of tension in this case is playing the role of that force which the glue must provide so it remains attached to the rod. If the glue is not that strong, this stone will no longer be attached to the rod and it will move off the circle. So when I apply this equation, equation 1 to this situation, it will become 18 is equal to 0.5, which is the mass, into 9.81, the value of G, plus 0.5, the mass again, radius is 0.2 into omega square. I have written this equation in the form F is equal to mg plus m r omega square, which is a modified form of mv square over r. So when I use these values here, it is easy to work out omega equals 13.2 radian per second. Let me explain once again what we have done here. The question was, we have a stiff rod here, and this stiff rod has a stone attached to this end with the help of a glue, and the force that it can provide, the maximum force it can provide, so it remains attached to it, is 18 Newton. So if they ask what is the position where this stone will most likely snap from this rod, that position is here. And for this position, we can write this equation that this 18 Newton must be equal to the weight plus mr omega square, which is another way of saying mv square over r, because omega is to be calculated here. So when we use the given values here, the mass, the length of the rod, and the force that this glue must provide to this stone so it remain attached, we can work out the value of omega in this way. This was a question that appeared in May, June 10. And this was the first variant of paper 4. So you can go through this question. The figure is provided in that question and the rest of the detail. So you can easily handle a question like this after you do it on your own. There is one more question that we can discuss before we complete our discussion of vertical circle, and for that I need to erase this all. The second problem, which appeared in October, November 2007, and this again was the first variant of paper 4. This was question 1 because in paper 4, the first question is also related to this topic, circular motion and gravitation. So this must be question number 1 when you see the paper. In this question, they have informed us that we have a string with its initial unstressed length equal to 13 centimeters. This is a string but when the same string is used with a mass attached to it, and this mass is 500 gram, there is a slight stretch produces in it, and the total extension, the total strength, total length now becomes 15 centimeters. That means the string is extended by 2 centimeters. Naturally, you can quickly work out what is the elastic constant for this string, K. If 500 gram is the mass that you have attached to it and it gets stretched, then this should be the force over extension. This is from Hooke's law. That means this is mg, 0.5 kg into 9.81 divided by 2 centimeters, so 0.02. This is the value of K that we will use later when we write the equation. Then this object, which is 500 gram mass, it is made to move in a vertical circle in this manner. This is the mass, the 500 gram mass, and it is whirled in this manner along the vertical circle. And when we move it in the vertical circle, its total length becomes capital L in centimeters, which means this will be even longer than this. 15 centimeter was the extension, was the length when we attach this mass to it, but when we give it a whirl along the vertical circle, it extends a little further, and we expect now that this value in centimeters is definitely going to be a little larger value than 15 centimeters. The question is about calculating this length L. What is the final length of this when we give it a whirl? An important thing to remember is that this will be at this position when this will have the maximum value of L, because when it moves to the top, the tension in the string reduces, probably becoming 0, and then it comes back to its same unstretched length, 13 centimeters. If they ask us to calculate omega for this purpose, the first thing is to calculate omega, the angular speed for this purpose. In this case, they have stated in the question that the object is made to move with uniform value of omega, uniform circular angular speed omega in this circle. So in order to calculate omega, we can assume the object to be here at this position. So at this position, I can write mg equal to, because mg will be acting vertically downward with no tension acting along this, so taken 0, and this m r omega square. Since this is 0, we ignore it. The mass will get cancelled here, no need to write the value of mass. This simply means that 9.81 will become equal to the radius, which here will be 13 centimeters, 0.13 in meters, times omega square. When I simplify this, it gives us the value omega equals 8.7 radian per second. We used this position to calculate omega because this value of L is unknown for this particular position. So what was easier and what was straightforward to apply the first equation that we started with for this position that we labeled as position B. This is the position at the top of the circle. So at this position, tension is taken 0, so weight alone is providing the force needed as the centripetal force. So mg can be equated to m r omega square at the top. Obviously, at the bottom, the things will be different. And now we are coming to that part of the question. The question number 2, in this question, the part 2, we may say, is about calculating the final length of this string. The equation for this position, as we already know, should be the force in this string, the tension, force in the string. This must be equal to mg, which is acting downwards, mg, plus m r omega square. This is the equation that we wrote for this position in our discussion previously done. The force in the string is given by the Hooke's law, which states that force of tension is K elastic constant times the extension in it. So Kx is that force. So the whole equation, if I write this Kx here, this is Kx. The whole equation now becomes, let's write mg first. This is 0.5 times mass into 9.81. This is the weight of the stone, plus 0.5 again, which is the mass, into the radius, which is the length actually. that is to be found, plus the value of omega that we just worked out. It was 8.7 radian per second squared, and this all should be equal to the value of K, which was mg, which is 4.9 divided by the extension produced 0.02 times the total extension L minus 13 the extension produced for this purpose can be taken equal to this, because 13 centimeter was the original unextended length. Expressed in centimeter, this should be written as 13 into 10 raised to the minus 2. Length, which was final length, we don't know what it is. I should write it L into 10 raised to the minus 2. So L minus 13 into 10 raised to the minus 2 is the total extension produced at the end. And this is the extension produced when we attached this weight to the string. So this part becomes K, this is K, and this part becomes the extension produced in the string. The left hand side of the equation is the two forces which must be equated to the force in the string. The force in the string is given by Hooke's law. So when I simplify this equation, I get the length nearly equal to 17.7 centimeter. Since this is the question that you can go through yourself with all the detail, I have made a slight changes in the values. You can go through these and do this question on your own with all this detail provided. This completes our discussion of circular motion. This was our last topic of vertical circle. In the next topic, we'll start gravitation. Thank you.